Greetings there, pre-calc students. Time for our last unit of this whole course. And as we've mentioned, this is going to be a calculus unit. This info comes basically from our calculus book that we use. And we're just trying to get everybody a little bit of a head start in this AP Calculus. Whether you're taking that class or not, this is a nice, suitable final unit for us in that it's somewhat challenging, but I think you'll be able to catch on pretty good and give you a nice introduction into calculus. So limits, you have an idea what a limit is when we talk about speed limits or age limits or term limits, that type of thing. But in math, a very important thing for you to keep in mind, I think, when we talk about limits, is a limit is a y value. So your answer for all of these types of problems will be y values. If you keep that in mind, that'll make things quite a bit easier. Here's the official definition or terminology we use when we do limits. And notice we read this, the limit of f of x. F of x will usually be a special function. Sometimes we'll actually put the function right in here, other times we'll refer to it. So the limit of f of x as your x values approach c. C will usually be a special number, an x value. And so as your x values get close to this particular x value, what will your y values equal? And we're going to look at several examples here, and I think you'll be able to catch on to this fairly soon. We'll look at, first of all, how this looks graphically with some given functions that are already graphed for us. Then we'll look at some algebraic ways to do it as well. All right, so here we go. The first example. So find the limit by graphing. Now notice what we have here. This is that limit notation that we learned about. This looks kind of strange. This is x approaches 1, then there's a little negative sign up there. That means from the left, or from the negative side of that. So, for instance, our first example here is x approaches 1 from the left, we'll say will be coming in this direction. The middle one then is x approaches 1 from the right. And then we have an overall limit, and we'll see some connection between these two. So keeping in mind here now that your limit is a y value, let's think about this first example here. So as your x approaches negative 1, so picture your x value is getting closer and closer to positive 1, but from the left, what are the y values getting really close to? And I think you can see that your answer here is going to be 2, right? The y values are getting very close to 2. Now let's move on to the second one. Here, as x approaches 1, the plus sign there means from the right. So coming in like this, what are your y values getting really close to? Once again, your answer is 2. Now, the overall limit then, that's considering both coming in from the left and coming in from the right. What do you suppose that's going to be? Well, yeah, it's also going to be 2. All right, so that seems pretty easy, I think. Let's go on to an example here. This one's slightly different. Here's our particular function again. Notice there's a break in the graph here, and we could call this a jump discontinuity. We'll talk more about discontinuities here later in this unit. But looking at, once again, we're still approaching 1 from the left, from the right, and then we're going to look at this overall limit. So, first of all, as it approaches 1 from the left, looks like, once again, my answer is going to be 2. Now keep in mind, there's an open circle here. It doesn't mean that the y value has to equal 2, but it means that it's just going to get very, very close to 2 as we keep going in like that. Now here's the change on this example. Notice as I come into 1 from the right, now my y value has been shifted up, isn't it? And so in this case, my answer will be actually 4. Now, here's the big question. We saw in our last slide that these two were the same. Then we did have an overall limit. What do you think the overall limit will be here? And maybe in order to help us out here, we're going to go to math movie, Mean Girls. And our actual answer here is the limit does not exist. The limit does not exist. And we'll emphasize this later, but the big idea here is that left-hand limit and right-hand limit must be the same in order for a limit to exist. All right, so let's do examples here. I'd encourage you just to pause the video and see if you could do this yourself. Now I do need to make one change here. This should be, I wanted this to be -8. So let's change all these to a -8 over here. And this will also be the f of -8. So that's my example. -8 then of course will be right here. And then the other one on the right will be +6. So if you want to pause the video and see if you can get that, we'll go over them here in a second. Alright, so let's take a look at this. So again, we're looking at -8 from the left. Again, if I follow that through, and I do have to follow along the function here. So it looks like my y value will end up to be -6. Again, it's not defined there, but that's what the y values are getting close to. Coming from the right then, again, you have to follow the function. So follow the function there, and sure enough, it looks like it's -6. Because these two agree, my overall limit is indeed -6. Now, this one right here, the f of -8, that's the actual value. That's the actual y value. And notice that's going to be a little bit different. That's -3. That's right where this dot is. That's the actual value of the function at -8. So this is kind of a key thing, that a limit can exist even if it's not defined at that particular value. All right, let's look at the next one then, looking at +6. So again, coming from the left like that, it looks like my answer is going to be 2. Coming from the right, so I have a little bit different path I'm following here. It looks like that's going to be, the y value again is 5. So the overall limit then, as x approaches, and by the way, I didn't want that to be -6, I wanted this to be +6, sorry about that. The overall limit then, we are going to have to say, based on our good friend Lindsay back there, D and E does not exist. Remember, these two must agree in order for a limit to exist. What would you say about the f of 6? Well, the y value, where it's actually defined, is up there at 5, isn't it? So there's my answers there. We'll practice on these in class as well, but I think you'll get the hang of it, and it's kind of a nice way to introduce you to the limit. Now, not only can I find limits just by looking at the graph, sometimes I can find them by just substituting a value in place of x. So for instance, in this particular case here, oh, and by the way, let's fill this out. This can be used as long as that function is, and the word I'm looking for here is continuous. Notice, if you think back to that last example, the place where we couldn't find a limit was where there was some discontinuity, where there was some break in the graph. But as long as the function is continuous, we can pretty much, all we have to do is substitute a value in for x. Now, this particular example here, x squared minus 3x plus 5, this is just going to be a parabola. There's no breaks in the graph at all. It's going to be a parabola that opens upward like this. You could graph this on your calculator. All you really have to do then, because it is so nice and continuous, is put 2 in place of x. So we have 2 squared minus 3 times 2 plus 5. So that's going to give us 4 minus 6 plus 5. So -2 plus 5 is 3. You could also verify that on the table of your calculator as well. So if a function is continuous and you're looking for a limit, all you have to do is substitute this value here in place of x. Alright, here. Sometimes though, a function will not be continuous, or something might be fishy. Here's a pretty famous function, or pretty famous limit. Make sure to get this down in your notes. The limit, as x approaches 0, of the sine of x over x. Now right away you see that something's a little fishy, because if you put 0 in place of x, in other words, if I try doing that substitution, that's not going to work here, is it? Because I'm going to get 0 in the denominator undefined. So here's where we use our calculator to help us out. So I entered the sine of x over x in my graphing calculator like this. Again, make sure you're in radian mode. I did change my window a little bit so I could see this graph pretty nicely. And again, if we think about our limits, as we're coming into 0 from the left, as we're coming into 0 from the right, you can see that even though it is undefined here at 0, we are going to get a pretty good answer. Also, to verify this, you might want to look at your table. Notice I went to my table set, and I just had the delta table or the change in table only go up by 0.1. So I could see right around 0 what's happening. Certainly at 0 there's an error, but if I look at the values right around 0, a little bit to the left and a little bit to the right, clearly we can see that particular value, and we would see that our limit in this case is actually going to be 1. So this is kind of a handy one to memorize. Actually, it might show up later on in this unit with some problems that we look at. Alright, so just in summary here for these limits, in order for an overall limit to exist, when we have interior points, that left-hand limit we say, I didn't mean to do that, I was going to use my little pointer thingy. Left-hand limit has to be the same as the right limit in order for that overall limit to exist. And we saw some examples of that graphically as well. And endpoints, we haven't talked about those very much, but endpoints must be defined in order for a limit to exist. And sometimes you'll hear that word closed interval. Basically, a closed interval means the filled-in circle. The notation would look like this, some square brackets. So for instance, if we look at this little example graphically that I have here, this is an endpoint here. Here's a case where the limit would exist because it is filled in on that endpoint. If we had a right endpoint here and it were an open circle, in that case we would say that the limit does not exist. So that's the deal with the endpoints. Alright, thanks for hanging in there. Kind of a longer video here, but good job. We'll continue to work on this in class. Thanks for listening, and we'll see you guys then.